Welcome back to the deep dive. Today, we are going to talk about something that, well, it sits in your pocket.
Probably buzzing right now.
Yeah, exactly, demanding your attention. We're looking at the deceptively simple world of the chat application. And I say deceptively simple because, let's be honest, we all totally take it for granted.
Oh, absolutely.
You pull out your phone, you open a green icon or a blue one or a black one, and you type lunch. You hit a button, and miles away, another phone lights up. It feels instant. It feels like magic.
It really is magic, but it's the kind of magic that requires just a tremendous amount of engineering rigor to pull off without the audience seeing the wires.
Right, and today we are ripping up the floorboards to see those wires. We are looking at a stack of documentation that details the system design of a mobile chat architecture. And the first thing that jumped out at me from these sources is that we aren't talking about a hackathon project here.
No, not at all.
We aren't building a little toy app for a college dorm.
No, the premise of this deep dive is scale. We're looking at the architectural decisions required for an app with 30 million daily active users.
30 million. That number terrified me when I read it because it changes the stakes completely. I mean, if I'm building an app for me and my 10 friends, I can code it badly. I can have inefficient queries. I can drain the battery. Nobody cares.
Precisely. If you write inefficient code for 100 users, you might lose a few milliseconds. If you write inefficient code for 30 million users, you are talking about massive server bills, widespread battery drain that gets your app uninstalled, or potential cascading failures that take down your entire infrastructure.
A thundering herd scenario.
Oh, yes. The nightmare of every backend engineer.
We will definitely get to that later. So
Right.
before we get into the nuts and bolts, the protocols, the databases, the retry logic, let's set the stage. The source material outlines a very specific scope for this design.
Right. Because in system design, scope is your best friend. You cannot build a massive app in a day. You have to carve out the core features. So for this deep dive, the rules of engagement are strict.
We are focusing purely on one-on-one text messaging,
Correct. No group chats yet.
which is a whole different beast.
It is. Group chats introduce a concept called fan-out, which complicates delivery receipts and notification queues exponentially. We are sticking to the fundamental atomic unit of chat, which is person A talks to person B.
And we are leaving out media files for now, too. No 4K videos, no high-res photos.
We're stripping it down to the core engineering challenge, which is text delivery.
Right,
But we are keeping the hard stuff.
right.
We need real-time delivery. We need online status indicators so you know if your friend is actually there. And crucially, we need historical access.
Offline first, that was a phrase that kept popping up in the reading. The idea that the app should work seamlessly, even when the internet is broken.
Which, let's be real, is half the time. Elevators, subways, spotty Wi-Fi. If your app only shows messages when you have a perfect 5G connection, it's pretty much useless.
Completely. And finally, push notifications. Because if the app is closed, you still need to know someone is trying to reach you. So that's the playground. Global scale, 30 million users, text messaging, offline capabilities. Let's start at the bottom of the stack.
The network layer.
Yes, the actual pipes that carry the data.
The nervous system of the application.
Now, the naive assumption, the one I think most people have, and I certainly had before I started looking into this, is that my phone connects directly to your phone. Like a walkie-talkie.
Right, a peer-to-peer connection.
Yeah.
And while that exists in some niche, privacy-focused technologies, it is absolutely not how modern chat apps work at scale.
Why not, though? It seems efficient. Cut out the middleman.
It sounds efficient on paper, but think about the reality of mobile devices. They move. You switch from your home Wi-Fi to a 4G network. Your IP address changes.
Oh.
If I'm trying to maintain a direct connection to you, and you walk out the front door, the link breaks. Plus, what if you're offline? If I send a message directly to you and your phone is off, the message is just lost.
It bounces into the void. So we need a mediator. We need a backend.
We need the canonical client-server model. You, the client, send a message to the server stores it safely, then the server finds the recipient and forwards it.
Okay, that sounds simple enough. I send to the server sends to you. But the source material highlights a massive asymmetry here. The first part, me sending to the server, is easy.
Very easy. That's standard web traffic. It's a basic request. You're saying, here is data, please take it. The server is passive, it just waits for you to talk to it.
The problem is the second part, the server sending the message to you.
The client-initiated dilemma. The web was built on HTTP. And HTTP is a request-response protocol. It's like a vampire, it has to be invited in.
I love that analogy.
It works. The server generally cannot just tap your phone on the shoulder and say, hey, take this message.
Yeah. So how did we solve this in the Stone Age of the internet? The source talks about polling,
Polling. The brute force approach.
which is basically the digital version of a kid in the back seat asking, are we there yet?
Exactly. Do I have messages? No. Do I have messages? No.
How about now?
Right. This is short polling. Your phone wakes up every few seconds, establishes a connection, asks the server, gets a negative response, and goes back to sleep.
And doing that for 30 million users?
Is suicide.
Yeah.
You are hammering your own servers with billions of useless requests. You're burning the user's battery. You're eating their data plan. It's incredibly inefficient.
So they tried to fix it with long polling.
Which is a clever hack, but still a hack. In long polling, the client asks, do I have messages? And the server doesn't answer immediately.
It just hangs.
It just hangs. It keeps the connection open, puts the phone on hold.
It leaves the line open until a message actually arrives.
Right. If a message comes in, the server flushes it down the open line and then closes the connection. The client processes the message and immediately opens a new connection to wait again.
It mimics real time, but under the hood, it's still HTTP. You're still tearing down and setting up connections constantly.
And that tearing down and setting up is expensive. It's what we call header overhead. Every HTTP request carries luggage.
Like what? Cookies.
Cookies, user agents, authentication tokens, content types. In long polling, you are resending that luggage every single time you reconnect. For a lightweight chat app, you want the data payload, not the packaging.
Which brings us to the hero of the modern era, the technology that makes real-time possible without the hacks. WebSockets.
WebSockets changed everything.
Let's unpack how this works mechanically, because it starts as HTTP, right? It's a wolf in sheep's clothing.
It's a Trojan horse, in
Yeah.
a good way. Client sends a standard HTTP request to the server, but it includes a special header. It says, upgrade.websocket.
It's asking for a promotion?
It's saying, I don't want a request-response interaction anymore. I want to open a pipe. If the server supports it, it replies with the 101 switching protocols status code.
And from that moment on, the HTTP rules are gone.
Gone. The connection remains open. It becomes a persistent bidirectional TCP tunnel.
Bidirectional being the key word.
Yes, full duplex. The server can push data to the client whenever it wants without waiting to be asked. And the client can send data to the server instantly.
And the luggage. Headers.
Gone. Once the handshake is done, you are just sending raw data frames. It's extremely lightweight. It keeps the radio active, but with minimal overhead.
So naturally, looking at this, my instinct and the instinct of many junior engineers, I assume, is, great, we use WebSockets for everything.
And that is a huge trap.
The source material is very specific about this. It suggests a hybrid approach.
This is a nuanced architectural decision that separates the pros from the amateurs. While WebSockets are amazing for receiving messages, they aren't necessarily the best tool for sending them.
This blew my mind a little bit. I have this high-speed, persistent tube open. Why wouldn't I just shoot my hello message up through it?
You can, but you have to think about scale and reliability. WebSockets are stateful. The server has to remember that this specific connection belongs to user A. That requires memory. It requires active management.
Okay.
If the connection drops, which happens constantly on mobile, you have to reestablish it before you can talk.
Whereas HTTP...
HTTP is stateless. You fire a packet at the server. Any server in your fleet can catch it, process it, and save it to the database. It doesn't need to know who you are beforehand because the request contains all the necessary info.
So for the uplink me sending a message, we use the sturdy, reliable, scalable HTTP REST API.
Exactly. It's much easier to scale the right path using HTTP. If 30 million people all send a Happy New Year message at the exact same second, it is much easier to spin up 1,000 HTTP servers to catch those requests than it is to manage 30 million WebSocket frames simultaneously.
And for the downlink receiving messages, typing indicators, read receipts, we use the WebSocket.
Because that needs to be server initiated. The server needs to reach out and touch you.
There's another concept mentioned in the advanced notes here, head-of-line blocking. This was another argument for why we might not want to stuff everything into one pipe.
Right. If you try to do too much over a single TCP connection and one packet gets lost, everything behind it has to wait while that one packet is retransmitted.
Like a traffic jam caused by one car breaking down on a single-lane road.
Exactly. By separating the sending over HTTP from the receiving over WebSocket, you actually decouple those risks. If your WebSocket is lagging or reconnecting, you can still send a message via HTTP. The send button still works, even if the receive pipe is momentarily clogged.
That is a critical resilience feature. Okay, so we have the pipes laid. We have a hybrid network layer. Now let's talk about where the data lives. The data layer.
The memory of the application.
When I hear big data, I think of cloud servers. Amazon DynamoDB, Cassandra, massive server clusters, and we're using those on the back end, sure. But this deep dive is about the client, the phone in your hand.
The edge.
And the recommendation in the text for local storage is SQL. Specifically, SQLite.
The industry standard for a reason.
I have to play devil's advocate here. SQL feels retro. It feels old. Why aren't we using something modern, like a NoSQL JSON store or a RUM database? Isn't chat just a stream of unstructured text?
But is it unstructured?
Yeah.
Let's look at the data model. You have a user. You have a conversation. You have a message.
Okay, true.
A message belongs to a conversation. A conversation involves users. This is the definition of relational data. It's a one-to-many relationship. One conversation has many messages.
So the data structure actually screams SQL?
It does. And more importantly, users expect to be able to search. If I want to find that message where I mentioned sushi 3 months ago, I need to query the database.
And SQL is the king of query.
It's what it was built for. SQLite can search that in milliseconds if it's indexed properly. If you stored everything in a giant JSON blob or a flat file, you'd have to load the whole thing into memory and scan it line by line.
Which kills performance.
And battery life.
There's another acronym that the source material waves around like a flag. ACID.
Atomicity, consistency, isolation, durability.
It sounds like something from a chemistry class, but in database terms, it means trust.
It means that when the app says, I saved this message, it is actually saved. Even if the battery dies a nanosecond later, even if the app crashes, SQLite guarantees that data integrity. You don't end up with half-written, corrupted messages.
Now, we have to talk about the physical limitations of the phone. I have friends, and I won't name names, who have chat histories going back 10 years. Gigabytes of text.
We all have that friend.
If we just keep saving to the database file forever, eventually the phone fills up. Or the database gets so big it becomes slow.
This is the storage management problem. You need an eviction policy.
Like a bouncer at a club, kicking people out when it gets too crowded.
Exactly. You have a few strategies here. There's the Slack-free tier strategy, which is a strict limit. We only keep the last 10,000 messages.
Simple. Brutal.
But effective. Then there's the WhatsApp strategy. Keep everything until the disk is literally full, then scream at the user to delete photos.
The source suggests a middle ground for us.
Right. We can use a least recently used eviction policy, an LRU. If a conversation hasn't been touched in a year, maybe we archive it or delete the local cache of it. The user can always refetch it from the server if they really need it.
But since we are text only for this specific scope,
text is incredibly cheap. You can store millions of text messages in a few hundred megabytes. So, honestly, for text, we can be greedy. We can keep almost everything locally. The performance bottleneck isn't usually storage size, it's indexing.
I want to double-click on that, indexing. For the listener who hasn't been a database admin, why does this matter so much for a chat app?
Imagine a library with 1 million books, but no Dewey Decimal System.
Yeah.
No alphabetization, just a massive pile of books.
Chaos, pure chaos.
If you want to find Harry Potter, you have to pick up every single book in the pile until you find it. That is what we call a full table scan. It's incredibly slow.
And on a phone, that looks like the app completely freezing while you scroll.
Right, an index is like the card catalog.
Yeah.
It tells the database exactly where to look. For a chat app, you absolutely must index the conversation ID and the timestamp.
So when I open a chat, the database jumps straight to the messages for that conversation, sorted by time.
Instantly. It's an O-log-N operation instead of O-N. For the computer science nerds listening, it's the difference between snappy and garbage.
Speaking of snappy, let's talk about pagination. Because we don't load the entire history at once.
No, you load chunks. Give me the last 50 messages.
Now, the classic way to do this is offset pagination. Give me page 1, then give me page 2. But the expert notes here say, do not use offset pagination for chat.
This is a really great point. Imagine you are looking at page 1, the latest 50 messages. While you are reading, a new message arrives.
Okay, I'm following.
The whole list shifts down by 1. Message 51 is now message 52.
So when I ask for page 2,
you might see a message repeated. Or you might miss a message entirely because the boundary shifted. Offset pagination is unstable when data is being added in real time.
so what's the solution?
Cursor-based pagination.
Explain that.
Instead of saying, give me page 2, you say, here is the ID of the last message I have. Let's say message 1050. Give me 50 messages older than 1050.
Because that ID never changes.
Exactly. Even if 1,000 new messages come in at the top, message 1050 is still message 1050. The anchor point is perfectly stable. It ensures you never miss a message and never duplicate one while scrolling.
It's these little details, cursor versus offset, indexing, ACID compliance that separate a professional app from a toy.
It's the difference between it works on my machine and it works for 30 million people.
Let's move to the heartbeat of the app, the message lifecycle. I love this section because it turns a split-second action into a dramatic 3-act play.
It really is a drama.
Act 1, the user input. I type pizza, and I hit the blue arrow. What happens immediately?
The app lies to you.
I knew it.
It's called optimistic UI. If we waited for the network to actually send the message and get a confirmation before showing it to you, the app would feel laggy. It would feel broken.
So we fake it.
We completely fake it. We immediately inject the message into the chat list. We render it, and this is key, we render it with a pending state. Maybe it's slightly grayed out or it has a little clock icon.
But the user feels like it's done.
The user feels satisfied. The app feels highly responsive.
Meanwhile, in the background, the real work begins. We create a message object. And before we send it, we save it to the local SQLite database with the status set to pending.
This is the persistence first rule. If the app crashes right now, we haven't lost the message. The next time the user opens the app, they will see pizza marked as failed or pending and they can retry.
Okay, Act 2, the transmission. The repository layer takes that message and tries to send it via our HTTP API.
Best case scenario, the server receives it, processes it, and sends back a 201 created status. The app gets that, updates the local database from pending to sent, and the clock icon turns into a check mark.
But we live in a world of elevators and tunnels. Let's talk about the unhappy path.
The request fails. The network throws an error.
So the naive engineer says, just try again.
And if that fails, try again, and again, and again.
This is the thundering herd problem we mentioned earlier.
Right. Imagine you have a momentary server blip, just a 1-second outage. During that single second, 100,000 users try to send a message. They all fail.
And if they all retry instantly,
then 100,000 requests hit the server at the exact same millisecond that it's trying to recover. You kick the server while it's down, it crashes again. The users retry again. You are now in a complete death spiral.
So we need exponential backoff.
We need to space it out.
Yeah.
Right? 1 second, fail. Wait 2 seconds. Fail, wait 4 seconds, fail, wait 8 seconds.
But the source material adds one more spice to this recipe, jitter.
Yes. Jitter is fascinating. Even with exponential backoff, if everyone fails at the exact same time, they will all retry at 1 second, then all retry at 2 seconds. You still get these massive waves of traffic.
Coordinated waves hitting the server.
Exactly.
Yeah.
Jitter introduces randomness. Instead of waiting exactly 2 seconds, I wait 2.1 seconds. You wait 1.9 seconds. Someone else waits 2.05.
You smear the traffic out.
You flatten the curve. It allows the server to digest the retries without getting overwhelmed by a single unified spike.
That is such a cool concept. Randomness as a safety feature. Now, Act 3, the zombie request, or what the text calls the idempotency problem.
This is the edge case that keeps architects up at night.
Walk us through the scenario.
Okay, you send pizza. The server gets it. It saves it. It sends back 201 created.
Success.
But you are on a train. The train goes into a tunnel after the server sent the response, but before your phone received it.
So the confirmation is lost in the dark.
Your phone assumes the message failed. It says, I never got a receipt.
So my phone, being a diligent worker, uses exponential backoff and sends pizza again.
Now the server receives pizza for the second time. If the server is dumb, it saves it again. It forwards it again.
And now my friend sees pizza twice in a row. And I look really desperate for pizza.
Or worse, if this was a payment app, you just sent $50 twice.
Oof. Yeah, that's bad. So how do we stop the duplicates?
Idempotency keys.
Explain the mechanism.
When your phone first creates the message locally, before it ever touches the network, it generates a unique ID, a UUID. Let's say ID ABC123.
Okay, got
It
it.
attaches that ID to the message. Message, pizza, ID, ABC123.
It sends it, the server processes it, the receipt is lost, the phone retries.
The phone sends the exact same packet again. Message, pizza, ID, ABC123.
And the server looks at the ID.
And it says, wait a minute, I have ABC123 in my database already. I processed this 3 seconds ago.
So it doesn't save it again.
It ignores the save, but, and this is crucial, it resends the success receipt. It says, yes, I got it, stop asking.
So from the phone's perspective, it feels like a successful send. From the server's perspective, it just deduplicated a request.
That is idempotency. Performing the same action multiple times has the exact same result as performing it once. It makes the system robust against network flakes.
I love that. It's like invisible armor for the data. Now, speaking of data messiness,
Huh?
ordering.
Oh, time. Time is the absolute enemy here.
If I send a message at 12:00 and you reply at 12:01, your reply should be below my message. That's basic conversation logic.
But what is 12.00?
The time on my phone.
Can we trust your phone?
I mean, it's a modern smartphone. It syncs with the internet.
Usually. But what if you manually set the time forward to cheat at a mobile game? Or what if your internal clock has drifted by 30 seconds? Or what if you are crossing time zones and the OS hasn't updated yet?
This clock skew.
And it is rampant. If we rely on client timestamps to sort messages, we are doomed. You might ask, how are you? And my reply, good, might appear above your question because my phone thinks it's 5 minutes ago.
That breaks the causality of the conversation.
It breaks reality. So, rule number 1, the server is the source of truth.
The server assigns the timestamp.
Or, better yet, a sequence ID. An auto-incrementing number, message 500, message 501, message 502. Integers don't care about time zones.
But wait, we have a conflict here. Remember the optimistic UI?
Yes.
I type message. It's on my screen. It hasn't reached the server yet. So it has no server ID. It has no server timestamp. How do I sort it relative to the messages that do have server IDs?
This is the hybrid ordering headache. The source material proposes a very clever solution.
Do tell.
You use 2 different sorting logics depending on the state of the message. If a message is pending, unsent, you use its local timestamp to float it to the bottom of the list. It's basically a guess.
Okay.
If a message is confirmed, you use the server ID or server timestamp. That is the fact.
And what happens when the confirmation actually comes back?
You swap them. The message transitions from the local sort bucket to the server sort bucket.
Does it jump around on the screen?
Ideally, no, because the now timestamp usually aligns with the end of the list anyway. But if there was a discrepancy, the server truth wins. The message might shift slightly to its correct canonical position.
It's a self-correcting list.
Exactly. It ensures that eventually everyone sees the exact same conversation history in the exact same order. Consistency is key.
Let's talk about catching up. The sync problem. I turn my phone off. I fly to London. I land. I turn my phone on. I missed 500 messages from a very chatty friend.
You've been offline for 8 hours.
How do I get those messages? Do I download the whole conversation again?
No, bandwidth is money. We use Delta Sync.
Delta meaning the difference.
Right. The client opens its local database and asks, what is the ID of the very last message I successfully stored? Let's say it's ID number 10,000.
Okay.
It sends a request to the server. Hello, I am user A. My last synced ID is 10,000. Give me everything after that.
And the server says, here are messages 10,001 through 10,500.
It sends only what you missed. It zips the new history onto the end of your old history. It's efficient, it's fast, and it works perfectly with that cursor-based pagination we talked about earlier.
We have one final massive component to discuss. The thing that actually makes the phone buzz when you aren't looking at it. Push notifications.
The wake-up call.
Now, we established that WebSockets keep the connection open while the app is running. But if I swipe the app away, if I force quit it...
The WebSocket is severed, the tunnel collapses.
Yeah.
You are offline as far as our server is concerned.
So how does the message get through?
We have to rely on the walled gardens. We have to go through Apple's APNs and Google's FCM.
Why, though? Why can't my app just stay running in the background listening for messages?
Battery life. If every app on your phone, social media, chat, games kept its own background connection open 204/7, your battery would last about 45 minutes. The radios would never sleep.
So the operating system acts as a tyrant.
A benevolent tyrant, mostly.
Yeah.
Apple and Google say, no, you cannot keep a connection open. We will keep one connection open.
A shared pipe.
Exactly. The OS maintains a single, highly optimized encrypted connection to Apple or Google servers.
So walk me through the flow. I send you a message. You are forced quit.
My server receives the message. It checks its internal connection map and asks, is user B connected via WebSocket? The answer is no.
Yeah.
So my server takes the message, wraps it in a special notification payload, and hands it to the push provider FCM or APNs with your specific device token.
Here, Google, wake this guy up.
Google pushes that packet down the shared system pipe to your phone. The Android OS intercepts it. It sees, oh, this is for the chat app.
It displays the banner, new message. It plays the ding.
Now, here is the really cool part. At this point, your app still might not be running. The OS handled the display completely on its own.
Really?
Yes. It's only when you tap the notification that the OS spins up your app process.
And then the race begins.
The app launches. It sees the notification intent. It immediately triggers that delta sync we just described. Hey, server, I'm awake. Catch me up. And boom, the message appears in the list.
It's incredible. It's a relay race involving 3 different massive corporations. Our server, the push provider, the OS manufacturer, all to deliver a lull in under 200 milliseconds.
Hey, lol is serious business.
It is. I want to zoom out for a moment. We've covered the network, the data, the life cycle, the sorting, the push notifications. The source material provides a diagram of the client architecture.
A clean architecture approach.
It divides the code into layers: UI layer, domain layer, data layer. Why do we need this complexity? Why not just write one big file and be done with it?
The God object. That is the path to absolute madness.
Why is it so bad?
Because things change constantly. What if we want to switch from SQLite to a different database next year? What if we want to switch from HTTP to gRPC? If everything is tangled together in one file, you have to rewrite the whole app.
So we separate concerns.
The UI layer is just for drawing pixels. It's dumb. It just says, I need messages.
It asks the domain layer.
The domain layer holds the business logic. What does it mean to send a message?
And it asks the data layer.
And the data layer is the worker. It's the repository. It decides, do I check the local database? Do I call the API? Is the cache stale?
The UI doesn't know how the data got there. It just knows it arrived.
Exactly. This makes the app highly testable. You can test the logic without needing a real phone or a live network. It makes the system robust.
One specific component caught my eye in the diagram, though: the image loader. We said we aren't doing media files, but we still need images.
Avatars.
Ah, of course, profile pictures.
Even a text app needs faces. And images are heavy. If you try to load 50 profile pictures on the main thread while the user is scrolling rapidly, the app will stutter. It will feel really janky.
So we need a dedicated component just for that.
An async image loader that fetches the image, caches it to disk, resizes it, and fades it in all without blocking the scroll. Again, deceptive simplicity. A rounded circle with a face in it is actually a complex, multi-threaded operation.
As we wrap up this deep dive, I am struck by how much we didn't cover. The source material explicitly scoped out encryption.
Which is the massive elephant in the room.
If we were building WhatsApp or Signal, we would need end-to-end encryption. E2E. How does that change things?
It breaks almost everything we just discussed regarding the server. In our current design, the server stores the messages. It can search them, it can read them. In E2E, the server is totally blind. It handles encrypted blobs. It cannot search. It cannot moderate content.
So the search feature has to move entirely to the client.
Correct. The client becomes the only place where the data is actually readable. It adds massive complexity to key management, device syncing, and search indexing. That is a deep dive for another day.
And group chats.
Fan out is the killer there. If I send a message to a group with 1,000 people, the server has to generate 1,000 individual push notifications. That requires high throughput message queues on the back end to handle the spike.
But for our mission, the one-on-one text app, we have built a tank.
We have. It's a system designed for failure. That's what I love about it. It assumes the network is trash. It assumes the user is impatient. It assumes the clock is wrong. And it works perfectly anyway.
That is the very definition of good engineering.
Absolutely.
So the next time you see that little sending spinner turn into a check mark, remember the journey that packet just went on. It negotiated a WebSocket upgrade. It survived a potential eviction policy. It fought through a shaky connection with exponential backoff and jitter. It deduplicated itself with an idempotency key, and it found its exact slot in history using a synchronized sequence ID.
It's a little miracle of distributed computing.
And here's a thought to leave you with. As our devices get more powerful and peer-to-peer mesh networks become more viable without killing the battery, we might eventually cut the server out entirely. The mediator might vanish, taking us right back to the walkie-talkie era, but at a global scale. Thanks for listening to The Deep Dive. Stay curious.
And stay connected.
See you next time.